Hey, welcome back to Calc 2. In this lecture, we're going to be looking at section 11.8 about power series. This is kind of the last tool we need to accomplish our goal of showing you where those polynomials I was coming up with that were so closely approximating the sine function. Those polynomials were really just sort of partial sums of a power series, a certain power series. So in this section, we're going to take a look at what power series are and how to find out where they converge and where they don't, what their domain is. So that's the second bullet point there. We're going to find their radius and interval of convergence. The first bullet point is telling you what a power series is and what I mean by the domain of it. All right, so let's just get going. One of these examples I have written out ahead of time, and the other ones I'll write with you, but if I'm ever going too fast in these videos, just pause it. Pause the video, go back, think about what I'm doing, take notes at your own speed so that you can digest this very important material. Okay, so let's just start with the definition. What is a power series? Well, it's a series like we've been talking about, but this series has a variable in it. This power series have centers. This one I'm writing down first is centered at 0. I'll tell you what I mean by a general center in a second, but power series is a function. It's function f of x, I'm going to call it, and it's given by an infinite sum. It has coefficients. These numbers, Cn, are called coefficients, and those coefficients are multiplied by just powers of x. So it's kind of like any given one of its partial sums is a polynomial function, yeah? If you ignore this dot, dot, dot over here for a second, it looks like that's a second degree polynomial. But there's a third term, c3x cubed, c4x to the fourth, and so on. So it never stops. But a power series centered at 0, sort of like a polynomial with infinitely many terms. And the coefficients, Cn, just matches the power of the variable x, x to the n. All right, so sometimes when you plug a number in for that variable, that series will converge. Sometimes it won't. The domain of the power series is just the set of those numbers. This fancy R is just the set of real numbers. So the domain is the set of x that when I plug x in for that thing and I get a numerical series like we've been studying, if that series converges, then x is in the domain. If the series diverges, then x isn't in the domain. Okay, let's take a look at an example. Here I've got a power series centered at 0. I just picked all the Cn's to equal 1. Every coefficient, 1 times x to the 0, 1 times x to the 1, 1 times x to the 2, 1 times x to the 3, and so on. That's just a geometric series. Yeah, if you take the ratio of any two consecutive terms, the next term over the previous one, that ratio is a constant x. So we know when that series converges. The geometric series test tells us that that series converges on the interval from -1 to 1. So the domain of that power series is the interval from -1 to 1. If you want to write it in interval notation, you'd write it with round parentheses because it diverges at both of the endpoints of that interval. Yeah, a geometric series diverges when the radius is greater than or equal to 1 in absolute value. By the way, that's another way to write this the -1, x between -1 and 1, or the interval between -1 and 1. Another way to write it would be to say that x is less than 1 in absolute value, right? These are three equivalent ways of writing the same piece of information that you can just draw a picture of it. Starting at 0, I'm taking the interval that extends out to -1 and 1 in each direction. So you can visualize the domain of that power function, power series, excuse me. It's the interval from -1 to 1. Okay, let's look at a more general definition. What do I mean by a power series centered at a number A? Well, if I'm talking about a power series centered at A, it's the same thing. It's a polynomial expression with infinitely many terms. So it's not really a polynomial, but it's sort of the nice way to think about it. But I'm not expanding it in powers of x, but rather x minus the center. So I still have coefficients, C0, C1, C2, but C1 is multiplied by x minus the center to the first. C2 is x minus the center squared. C3 times x minus the center cubed, and so on. All right? So that's what I mean by a power series centered at A. So hopefully it makes sense that if A is equal to 0, this expression just becomes the one that was written before. Stop the video and go back and look at it. If A is equal to 0, instead of writing x minus 0 everywhere, we just write x. Okay, same definition for domain. You plug an x value into this series and it converges, it's in the domain. If it diverges, it's not. There's one x value that we're guaranteed will always be in the domain, and that's the center itself. Because if I plug in x equal a into this series, then every single one of its terms is equal to 0, except for the one that corresponds to n equals 0, right? Because x minus a to the 0 is 1. If you plug in x equals a into this expression, then you end up just getting c0 plus 0 plus 0 dot dot dot. Well, that series certainly converges. It only has one non-zero term. It's a finite sum. It converges to the term that's in it. So the center of a power series is always in the domain of the power series. Okay, I think it's important to note that there's no such thing as a power series that doesn't have any numbers in its domain. The center is always in the domain. Let's look at an example where I've written out. So I'll go fast through this one, and then example 2, I'll write with you. All right, so let's take a look at this power series. Let's find its domain. So the C sub n's, if you like, are n factorial. So I'm starting at n equals 0. By definition, 0 factorial is equal to 1. So when n is 0, I get 1 times x to the 0 for the first term. When n is 1, I get 1 times x to the 1. When n is 2, I get 2 factorial times x squared. But 2 factorial is 2. 3 factorial times x cubed. 3 factorial is 6, and so on. It's an infinite sum. All right, and the question I'm asking is, for which x, when I plug into that sum, does the series converge? Well, I'm going to use the ratio test to answer that question, because if x isn't 0, that series will converge absolutely if this ratio this limit rho is less than 1. The series diverges if it's bigger than 1. If the ratio is equal to 1, then we have to check those as special cases. But so I'm going to just use the ratio test. So I'm looking at my nth plus first term. So that's replacing n with n plus 1 in my series term. So I have n plus 1 factorial times x to the n plus 1 divided by the nth term, n factorial x to the n. The absolute value of all that stuff. Yeah, don't forget the absolute values. So the usual things, splitting off the n plus 1 from the factorial, splitting up the exponential, n factorial over itself is 1, the exponentials cancel. We end up just getting n plus 1. I don't have to write absolute values around it because it's positive, times the absolute value of x. But it doesn't matter what x is, that limit is always infinity. Yeah, so that series is going to diverge for every value of x, well, except for the center. So the domain of that power series is just one single number, the center. It's as small as it can possibly be. Let's look at a second example. I'd like to find the domain of this series. What is the center of it? It's visible in the expression. Maybe stop the video for a second and ask yourself, can you say what the value of A is? What the center of that series is? The center is revealed by, you're looking at x minus it to the n. So in this series, the center must be a equals 3. Okay, so we know that that series converges when you plug in x equal 3. If you plug in x equal 3, all but one of the terms is going to be 0, and the series is going to converge. But I'm wondering, are there other points in the domain? So we're always going to answer this question with the ratio test. Because if that limit, rho, of the nth plus first term over the nth term in absolute value is less than 1, it's guaranteed to converge. If it's bigger than 1, it diverges. If it equals 1, well, we have to check that out as a special case. So let me show you the procedure. So you're going to start a problem like this by using the ratio test. We're going to take the limit as n goes to infinity. Don't forget the absolute values of the nth plus first term. So I'm replacing n with n plus 1. N plus 1 is n plus 2. And then I'm dividing that by the reciprocal of the nth term. That's the same as dividing by the nth term, right? And then the usual cancellations here, I'm going to split up that x minus 3 to the n plus 1, right? So I've got n plus 1 factors of x minus 3 in the numerator. I've got n factors in the denominator. Well, that's going to leave me 1 in the numerator. So I'm not going to write the details here to save some room. So I've got the absolute value of, I'd have 1 factor of x minus 3 surviving in the numerator. And then I've got, well, n plus 1 over n plus 2, which doesn't simplify at all. Let me come back over here and split that up. The absolute value of x minus 3 is a constant with respect to n. So I can pull it through the limit. It doesn't depend on n. So the limit I'm calculating is just the limit, x minus 3 in absolute value times the limit of n plus 1 over n plus 2. I don't have to write absolute values around that because n plus 1 over n plus 2 is positive, right? That limit is 1. What limit you say? The limit as n goes to infinity of n plus 1 over n plus 2 is 1. So we just end up getting x minus 3. Yeah. So the ratio test says that this series is guaranteed to converge if that is less than 1. If that limit is less than 1, then we converge. So I'm setting this equal to 1, or sorry, setting it less than 1 to find a condition that guarantees me that this series will converge. If that limit, the absolute value of x minus 3, is bigger than 1, the series is guaranteed to diverge. If it equals 1, the ratio test has failed, and so we have to check that out as a special case. But so far, we can say, if we sort of drew a little picture here, we mark the number 3 on the number line. When you read absolute value of x minus 3, it's very important that you understand that this means the distance from x to 3. That's what absolute value of a difference does. It measures the distance. So if you think about it like that, you don't have to do a bunch of fancy algebra. I'm just saying the distance from x to 3 can be no more than 1. Well, you can write down exactly what numbers would satisfy that. You can move up to 1 unit to the right of 3, so you'd have to stop at 4. I'm using an open parenthesis because I have a strictly less than. But you could also move to the left of 3 by 1. You could go down as far as 2. Yeah. So what we're writing up here, this x minus 3 is less than 1 in absolute value, that corresponds to the open interval between 2 and 4. That is guaranteed to make our series converge. We are guaranteed to converge if we're between 2 and 4. And for that matter, if this ratio, if x minus 3, the distance is bigger than 1, then we're guaranteed to diverge. Yeah, because if that ratio is bigger than 1, the ratio test says that we diverge. So numbers out here on the number line, numbers that are less than 2 or bigger than 4, we know that that's going to diverge. All right, but what the ratio test would fail at is, what about x equals 2 and x equals 4? Because the ratio test fails. It doesn't tell us. So what we have to do is check those out as separate cases. We have to check those things out as separate cases. Let me grab my series here so I don't have to write it again. It's a little bit lazy, but I'm going to do it. So let me show you the technique. Just picking these one at a time. Let's pick x equal 2. All right, let's pick x equal 2. If we let x equal 2, then what does this series become? Well, 2 minus 3 is negative 1. So we end up getting the sum as n goes from 0 to infinity of negative 1 to the n over n plus 1. And the question is, does that series converge or diverge? This is the moment when I can finally tell you why I needed you to learn all of those series tests in chapter 11, because when we go to do this, the ratio test is the only test that we need to determine this kind of interval piece of the domain, but we're always going to have to wonder if the endpoints are in there. And when we plug in an endpoint, we get some series, and we have to note, does that series converge or diverge? This series converges by the alternating series test. I'm not going to include all the details of the verification of that here, but the terms are alternating, and the sequence 1 over n plus 1 decreases to 0 as n goes to infinity. So this thing converges by the alternating series test. So x equals 2 is in the domain. I'm going to alter my picture here for a second. I put a round parenthesis up there. I can now go back and say, no, it's actually a bracket, because 2 made it into the domain of this function. I was coloring the domain red, so let me color 2 red. If I plug in x equals 2, this series converges. I got to ask the same question about x equals 4. Stop the video and see if you can answer the question yourself before I do it. I have to take x equals 4 and plug it into this series and see what I get. So again, let me be a little bit lazy here and just copy this. Put it down there, and let's do the same thing. If we let x equal 4, well, what does this series become? 4 minus 3 is equal to 1. Any power of 1 is still 1. So I just get the series 1 over n plus 1, yeah, starting at 0. If you write out some terms of that, that's 1 plus 1/2 plus 1/3. That's the harmonic series. It diverges. It's the divergent harmonic series, right? So x equals 4 is not in the domain. Oops, excuse me. X equals 4 is not in the domain. So we've completely answered the question here. I'm just going to scroll back up to this picture that x equals 4 should be around parenthesis. The domain of this power series is the closed, half-closed interval from 2 to 4, including 2, not including 4. You give me an x in that interval, this power series converges. You give me an x out of that interval, it diverges. Cool. Let's do another one. You can pause, take a break if you're tired. Here I've got a power series. This time my c sub n's are 1 over n factorial. All right, and I want to find the domain. So we're going to do the same thing. We're going to use the ratio test. Can you see the center? What's the center of this power series? It's x minus what to the n? Here the center is, can you say it? 0. This power series is centered at 0. Ratio test. I'm going to take a look at the limit as n goes to infinity of the absolute value of the nth plus first term, replacing n with n plus 1, divided by, I'm going to multiply by the reciprocal of the nth term. Right? We've done a lot of these ratio tests, a lot of these factorial simplifications. So make an appointment with me or come to an office hour or come to class. But to keep these videos short, I'm not going to throw in a lot of tedious algebraic computation because if you've done a bunch of these, you can see how it's going to simplify. Yeah, the n plus 1 factorial over n factorial is going to leave you a 1 over n plus 1 downstairs. X to the n plus 1 over x to the n leaves you an x upstairs. Once again, x in absolute value doesn't depend on n, so it can come through the limit. So we just have to take the limit as n, as n goes to infinity of the expression 1 over n plus 1, and we multiply that limit by x. Well, 1 over n plus 1 goes to 0 as n goes to infinity, and x, the absolute value of x times 0 is 0, regardless of what x is. Right? So this series converges for all x. All x in the real numbers. That's all I mean when I write this. All real values of x. So its domain as an interval, the domain is really just the interval from minus infinity to infinity. It's all real numbers. If you want to write that, well, as an interval, you should write it like that. But that's what I mean by this symbol r. This fancy r is just the set of all real numbers. So this power series will converge no matter what x you put into it. Interesting. Cool. Well, so these three examples that we've looked at, they kind of illustrate the three possibilities. I'm going to do a little bit of scrolling here on you, sorry. But in the first example that we looked at, we had a power series. It only converged at its center. Every power series converges at least at its center, but this first example, that was it, yeah? And then we had another example where the power series, of course, it converged at its center, but then there was some distance that we could move away from the center and it would be guaranteed to converge. That distance was 1 in the second example. And then we had to check the endpoints. So in this particular example, it turned out that the left endpoint of that interval was in there, but the right endpoint didn't make it. And then in the third example, the series just converged no matter what x was. Yeah, so you can think about that as the distance that we can move away from the center was sort of infinite, if you like. Yeah, the center of this series is 0, and you can move as far away in either direction from the center as you want, and it's still going to converge. All right, so that's basically the nature of any power series. I'm going to scroll down here for a second because I've clipped something out of your book. That's a theorem. I'm not going to give a proof of it, although I just kind of alluded to how you would prove it. You would use the ratio test. But if somebody hands you a power series, let's kind of walk through this theorem. It's given center is A. There's three possibilities for what its domain is. Yeah, like in our first example, one possibility is that the series will converge only at the center. So if you have some notes here, this is like our example 1 above. Our series converged only at the center. A second possibility is that the series just converges for everything, that every single x, that was like example 3 above. Or there's some positive number r. There's some positive number r. That number r is called the radius of convergence of the power series, or just ROC, if you want to abbreviate it like that. There's some positive number r that the series will converge if x minus a in absolute value is less than r, and it diverges if it's bigger than that. You find that r with the ratio test. And in our third example, our second example, so like in example 2, the radius was 1. We could move 1 unit away from the center, which was 3. Go out to 4 or down to 2. Okay, so every power series has this so-called radius of convergence. This radius of convergence, ROC. And you can even think of the first case when it only converges at a single point. Just think of that as the radius of convergence is 0. You can't move away from the center at all if you want to converge. Yeah. Example 3, where we got all x's, just think of that as the radius of convergence being infinity. You can move as far away from the center as you want. All right. The domain of a power series is the interval of convergence. You take that center and subtract and add the radius to get an interval. But what these 4 possibilities are showing, let me just scroll and show you the picture at the same time. In that interval, you might not have either endpoint. You might have one of them. You might have the left one. This is like our example 2, where the left endpoint made it in, but the right endpoint didn't. Or you might get them both. Yeah. How do you tell? After you know the radius of convergence, you have to take those 2 endpoints one at a time, plug them in, and see if the series converges or diverges. So here's the book's picture of what I was drawing above. They've already highlighted that, given a power series, you calculate its radius of convergence, you can move that distance away from the center to the left or the right. So once again, please notice that they're writing this in absolute value, but I want you to think of this as the expression, the distance from x to a is less than r. Because if you think about it like that, then the picture that you're looking at is kind of obvious. You start at a and you can go r units to the right. If you go r units to the right, you would be at a plus r. You could also go r units to the left. You're at a minus r. You're guaranteed to converge in that interval. The ratio test guarantees it. In fact, it converges absolutely. Outside that interval, the ratio test guarantees you that you will diverge. I colored that in blue above. Let me do it the same. Over here, you're guaranteed to diverge because the ratio test's limit is bigger than 1. But at the endpoints, it depends. You have to kind of think about it. Every series kind of has its own personality. You have to check those endpoints individually. And once again, it's going to be one of 4 cases. Neither endpoint makes it in. The right endpoint does, but the left endpoint doesn't. The left endpoint makes it in, but the right endpoint doesn't. Or maybe they both make it in. You have to check. Okay, let's take an example. So this time, instead of phrasing it as the domain, I'm trying to use our new language. Let's find the radius and interval of convergence for this power series. Okay. What are the C sub n's? The C sub n's are the numbers that are multiplied by x minus the center. So I just kind of outlined the C sub n is n over 3 to the n plus 1. That's my coefficient. What's my center? Can you say it? This has to have the form, listen carefully, x minus the center to the n. So what number is that x minus? It's not 2. It says x plus 2. So the center here is negative 2. Yeah, that looks like x minus a minus 2. Okay, let's use the ratio test. We're going to use the ratio test to find the radius of convergence of this power series. Once we know the radius of convergence, then we'll know the endpoints to check. We have to do 2 series tests to check them. So let's do it. So we got to take the limit as n goes to infinity of the absolute value, replacing carefully n with n plus 1 everywhere. That exponent down there would be n plus 1 plus 1 or n plus 2. And then divide by a sub n. I'm going to multiply by the reciprocal. The cancellation patterns are always kind of the same rules. Exponent rules, factorial cancellations. There are no factorials here. So what do we get? I've got I got n plus 1 factors of x plus 2 upstairs and n of them downstairs. So that's going to leave just 1 upstairs, and I'll leave the absolute values around that. Everything else, the 3 to the powers of 3, n plus 1, those are all positive. I don't need them. The powers of 3 will cancel. I've got n plus 1 factors upstairs and n plus 2 factors downstairs, so that leaves me 3 of them down there. And then what do I have? I've got an n plus 1 over n. This part doesn't have any n's in it, x plus 2 absolute value over 3, so I bring it through the limit. X plus 2 over 3 can come out of that limit, so we just have to take the limit as n goes to infinity of n plus 1 over n. Okay, that limit is 1. N plus 1 over n goes to 1, so we end up getting x plus 2 in absolute value over 3. Okay, and now I'm setting this. If I want to converge by the ratio test, that has to be less than 1. I'm always going to set that less than 1. But this time it's a little different. I have to do some algebra to solve for my x minus the center in absolute value. In particular here, I need to multiply both sides by 3. So this series will converge if the distance from x to -2, watch what I say and what I've written, the distance from x to -2, yeah? You need to be able to read that as the distance. It can't be any more than 3. So there is your radius of convergence. R is equal to 3. And I think rather than doing a bunch of fancy stuff with absolute value algebra, you just draw a picture. You take your center, -2, and you count. Where can you go if you move 3 units to the right of -2? Well, you could make it all the way to -2 plus 3. You could get to 1. How about going to the left? You could subtract 3 from -2. You could get as far away as -5. So we know that this series is guaranteed to converge on the interval that I just painted red. The open interval from -5 to 1, we're guaranteed to converge. But we have to check our endpoints. So we know the radius of convergence. The radius of convergence is equal to 3. But for the interval of convergence, well, I almost know it. What I don't know is -5 in there or not? Is 1 in there or not? So we have to test those, okay? So I'm just gonna come back up here and grab a copy of my series. Save me a little bit of writing. And we have to test them. You don't have to test them in any given order. I usually work left to right. So I'm gonna take the endpoint -5. And what am I doing with that -5? I'm plugging -5 in right there for x. So what is -5 plus 2? Yeah, -5 plus 2 is -3. So if we put that in, we get the sum as n goes from 0 to infinity of n over -3 to the n over 3 to the n plus 1. And I'm going to clean that up a little bit. That's the sum as n goes from 0 to infinity of n times -1 to the n. I'm going to split this -1 to the n times 3 to the n. And in the denominator, I've got 3 to the n plus 1. All right. So that's, if we cancel 3 to the n in the numerator, 3 to the n plus 1 in the denominator, it just leaves me a 3 in the numerator. So I have to look at that series and determine, does it converge or does it diverge? So you can stop the video. I think you should stop the video and try to answer that question yourself. You have all the tools you need for it. So when I'm looking at that series, what I see is that if I ignore the -1s If I ignore the minus ones and I just take the limit as n goes to infinity of n over 3, that limit's infinite. So this series diverges by the divergence test. Okay, so x equals minus 5 did not make it into the interval of convergence. Now we have to do the same thing for x equal, what was the other endpoint? 1. So if we take our series, let me do it down here where I have some more room, and we let x equal 1, well, 1 plus 2 is 3. So we get the sum of n times 3 to the n over 3 to the n plus 1. Again, by the rules of exponents, a lot of those 3's cancel. So we end up just getting n over 3. This series diverges by the divergence test. So in this example, our interval of convergence, neither endpoint made it in. So the domain of this power function is just the interval from minus 5 to 1. All right. So I think we've succeeded in our goals. Let's just go back to the top here and see. What I tried to do in this lecture is I tried to tell you what a power series was and what I mean by its domain, okay? And then I tried to show you that a power series has a radius and an interval of convergence, and I tried to do several examples to show you how you can use the ratio test together with your other series tests. Ratio test tells you the radius of convergence. Other series tests tell you whether the endpoints make it in to find the interval. Thanks for listening.